I've been thinking of the real plane, so R2, and there's a whole theory of indices for other types of geometric situations. It's called Poincaré-Hopf index theorem. So there could be other types. So if you have other topological two-dimensional spaces, like spheres or torus, then other things can happen. This gives an idea of the index of a space. Basically tells you if there are fixed points or not. Like, do there have to be fixed points? So the sum of fixed points over the entire space must equal the index for the space itself. For R2, the index is undefined, as this only relates to compact two manifolds. But for the sphere, so this is the usual sphere, index equals +2. For a torus, which is S1 cross S1, index equals 0. If you're wondering, okay, what's the plane? There it is. What's a sphere? It's this thing. What's a torus? It's fun to draw a torus. Okay, what are the implications of this? The sum of the fixed points, indices, must equal the index of the space itself. The sum of indices of fixed points in a topological space must equal the index of the space itself. So what this means is if you have a sphere, you must have some fixed point. It means all vector fields on the sphere must vanish somewhere. And this has been put in a few different ways that are kind of interesting. Like you can't comb a coconut. What's a coconut? A coconut is, topologically a sphere, and think of the hairs of the coconut are vectors. So if you try to comb them, you can't properly comb it. There's always going to be a spot where you can't comb it. You'll have to have a cowlick. So this has been called the you can't comb coconut. Just for example, to give you an idea of a system, if let's say I had a ball and I dripped something on it like honey, and I started from the top and it just started dripping down. Well, that top point would be a fixed point of index 1, and then wherever this sort of drips down to and collects, that would be another fixed point of index 1. So index 2 total. It's fun at this point to show pictures of people trying to comb coconuts. I couldn't really find that. Found some other things. It's also called the hairy ball theorem. Here's what I mean. This is a baby's head, right? You try to comb a baby. And it's not now a complete sphere. It's more like a hemisphere. There's always going to be this spot where things just aren't working out. You can't comb there. Things swirl around. In this case, this child has it looks like an unstable spiral. And there might be more than one. Like, here's somebody trying to comb a sphere. They tried to comb a sphere, and then if you just sort of start with arrows or lines that are tangent to a sphere and try to comb this thoroughly, well, you're going to find there's places where everything accumulates, and the vectors are just going to have to point up, meaning they're not tangent anymore. So you can't comb. So those are the top and the bottom here would be places where it didn't work out. And so each of those would be fixed points of the vector field with an index 1, meaning the total index is 2. Here's an example of a flow on the sphere with just one fixed point. But if you were to look carefully, this fixed point has an index of 2. And then here's just the view of it. So there's only one fixed point. It's like we've done all the combing in such a weird way that everything just sort of wraps. Like that's the same fixed point. So that is a fixed point with an index of 2. So you can get away with one fixed point, but it'll look kind of weird. Here's a hairy donut. And then, like I said, it turns out, yeah, you can comb a donut. You could just be combing it in one direction. There's no place where the vectors will all sort of bunch up, so you can get away with it because the torus as a topological object has an index of 0. So here's a vector field, for example, that has that doesn't vanish anywhere. There's no fixed points. And you might wonder, okay, what are the implications of this? I actually did a my earlier years, I was at University of Southern California and was studying flows on a sphere. And we had in mind something like the weather, and the weather is, if you think of just one spherical shell, it's like a vector field on the sphere. So for the sphere, the wind on the Earth has to vanish somewhere, according to this theorem, at least one place, and usually more than one place. So I'm plotting here. This is showing some, maybe it's better. No, you can kind of see here. These are streamlines on the sphere. So they're kind of the same kind of streamlines you would see in weather. But this is for some idealized case where we have a few hurricanes. And by hurricanes, I mean point vortices. And anytime these curves seem to intersect in what looks like a saddle point, it is a saddle point, and so on. And these things evolve in time. But up here at the top, you can see the bifurcations of this system were constrained by, here I didn't mention Hopf, but the Poincaré index theorem. So the number of C, in this case centers, minus the number of saddles equals 2. Now, why is this? Because each center has an index of +1. Each saddle has an index of -1. And the sum of the indices of all fixed points must equal the index of the space. In this case, it's a sphere, so 2. Of course, we do this stereographic projection because it's hard to look at spheres. You can't see all sides at once. But yeah, things have to merge and so on. And then, yeah, you don't need to see the rest of that. But that gives an idea of how this gets used. So you can't comb a coconut.